All right, pre-AP Algebra 2. Let's get our lesson 6 on. Here we go. So we're going to actually wind up deriving some really cool polynomial identities, which is some pretty big boy and girl math, I got to say. So let's get this thing going. It's going to be awesome. Here we go. So let's go ahead and start by just finding some quotients. I am seeing that I can use the synthetic division, so I'm going to do that. Whenever I can use synthetic division, I do, because it's awesome, right? So again, I'm going to put a positive 3 over there on the left-hand side, because my denominator has a negative 3 there, right? So it's always going to be the opposite side. That 1, 0, and negative 9 represent 1x squared, 0x, and negative 9x to the 0 power. All right, I'm going to drop down the 1, multiply. 3 times 1 is 3. I'm going to add, I'll get 3 here. And then I get 3 times 3 is 9. And then negative 9 plus 9 is 0. Remember, this one, my degree is 2, so this must be degree 1, right? So that means that my result is, this is all equal to, and I should use an equal sign here, fantastic. That's going to be x plus 3. Cool, let's do it again. And what do we notice is happening? A pattern that's forming. Think about that as we're going through that. What pattern is forming here? So I've got 1x cubed, 0x squared, 0x, and negative 27. That's the way I'm going to set up my synthetic division. I'm going to go ahead and drop my 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. 0 plus 9 is 9. 3 times 9 is 27. Negative 27 plus 27 is 0. And so then my result is that this is going to be x squared plus 3x plus 9. Interesting. Interesting stuff. Let's continue and see if we can get, see what happens with this pattern. We see a pattern forming already. Let's see what's going on. So let's use synthetic division again to find this quotient. So let's see. That's x to the 4th, 0x to the 3rd, 0x squared, so 0x, and negative 81 x to the 0, right, if you will. Drop down the 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. 0 plus 9 is 9. 3 times 9 is 27. 0 plus 27 is 27. And 3 times 27 is 81. 81 plus 81, negative 81 plus 81 is 0. And what is going to be our result? We are going to get, let's see, first of all, our degree was 4 of our numerator, right? So we're going to start with the degree of 3 for our answer, or for our quotient. So we'll have x cubed plus 3x squared plus 9x plus 27. Interesting. We're going to actually wind up coming up with a formula that matches this pattern. Let's look at the pattern real quick. We've got x plus 3, then we wind up with x squared plus 3 plus 9, and then x cubed plus 3 plus 9 plus 27. And the reason why I'm only mentioning the coefficient is because that's where the pattern is occurring, or the pattern that we could really grab onto. So I didn't mean to throw you off by only mentioning the coefficients, but I'm really just looking at the pattern for right now. So let's continue on with this, and we'll wind up doing some pretty cool math by the time we're done with this. So we're going to find patterns, we're going to use patterns to predict each quotient. and we're going to explain how we arrived at our prediction, and then we're going to test it by applying the reverse tabular method for long division. All right, so how in the world would we use that same pattern? Well, here we have some squares, right? In our numerator, we have x squared. And then isn't 144 just 12 squared? So if we were to follow our pattern that we had before, we should get that this is x plus 12, right? Okay. I don't want to use reverse tabular method or long division to check it because I can save myself a bunch of time by using synthetic division. And indeed, it is true. Okay. Continuing on, how would we use a pattern here? So it looks like now I have a cube. Right? I have two cubes here. I have x cubed and 8, which is 2 cubed, right? And then I have 2 on the bottom, which happens to be the cube root of 8. Interestingly enough. So if we're going to follow our same pattern that we found before, it should be the case that this is x squared plus 2x plus 4. What's going on? What's going on? What's the pattern? Right here, right, I have this 2. It turns out that the coefficient of this is 2 to the 0 power. The coefficient of this one is 2 to the 1st power. And the coefficient of this one is 2 squared. Oh, that's the pattern. Let's use that to figure out the next quotient. Okay, well, if that's true, if we're looking at, right, we're using 5 as our number in our quotient, we see that the degree of the numerator is 3, so that means that this degree must start off being a 2, yeah? And then what's going to go here? 5 to the 0 power, right? All right, what's next? 5 to the 1st power. What's next? 5 squared. Okay, well now let's take this all the way and apply it to x to the 6th minus 1. All right, where we're looking at different powers of 1 as we go out with this. Now, our degree of our numerator is 6. So we're going to have to start with x to the 5th, right? And remember, this is 1 to the 0 power, right? And then we're going to have x to the 4th. And this one is 1 squared, but wait, okay. So essentially, our coefficients are always going to be 1, right? So let's continue on. So x to the 3rd, x squared, x, and then 1, because this is 1 to the 0. Sorry. Okay. How about 1 to the 5th power, right? Because our coefficient of x cubed should be 1 to the 3rd power. Our coefficient of x squared should be 1 to the 4th power. And then we're at 1 to the 5th power and 1 to the 6th. My bad, I skipped this. This should be 1 to the 1st power, sorry. this one should end with 1 to the 5th. All right, that's better. All right, moving right along. Ooh. What is the quotient of x minus a what's the quotient of this thing? Let's go ahead and use, I think I feel like long division. All right, so here's our divisor. That is an a, and our dividend. So x squared minus 0x minus a squared. Perfect. All right, so we'll set it up like this, right? And x will wind up being our first term when we divide, right? I'm thinking to myself, hey, what do I need to multiply times x, right, to get x squared? So, and then I'm going to multiply that back out. X times x is x squared, and then x times negative a is going to be negative ax. I'm going to change the signs and add. Those are going to cancel, and I'm going to wind up with a positive ax here, and I'm going to drop down my a squared. What do I need to multiply ax by to get, what do I need to multiply x by to get ax? Well, it's just going to be a. And now I'm going to multiply it back out. A times x is ax, and a times negative a is negative a squared. And when we change the sign and add, I wind up with a 0 remainder, which means that that's actually equivalent to x plus a. Awesome. All right. So let's go ahead and find these quotients. Shall we use reverse tabular method just to mix it up? Why not? All right, first I need to determine my rows and columns. So I'm going to have 2 rows and 3 columns. All right, I'm going to have x cubed. And I need to have placeholders for these, right? So there's no x squared term. There's no x term. But our constant term is negative a cubed. Could be any number a. Over here, we're going to have x, and we're going to have a negative a. And let's do this thing. So x cubed goes there. Which means that this has to be x squared. And x squared times negative a is negative ax squared. So that means this has to be positive ax squared. Which means that this has got to be ax. Alright, when I multiply this out, I wind up with negative a squared x. Okay, which means that this has got to be positive a squared x. Which means this guy is going to be a squared. And a squared times negative a is going to be negative a cubed. Which is awesome, right? When those two values match up, that means that I have no remainder, and there shouldn't be any remainder with these. So then, what did we find out? We found out that that quotient is equal to x squared plus ax plus a squared, and again, it appears that a pattern is forming. Can I just go ahead and use that pattern to find this next quotient? I think so, right? Okay, look. For a, it started with, we were dividing a third degree polynomial, now we're dividing a fourth degree polynomial. So you can imagine that this here is going to be x cubed. All right, what's going on? What are my coefficients in this one so that we can find a pattern? It looks like this is a to the 0. That's a to the first power. And that is a to the second power. Ooh. All right. Cool. And what's going on with x, right? For our x, this is x to the second power. This is x to the first power. And it turns out that there is an x there. It's invisible because it's x to the 0 power. So look at that. Our powers of a are ascending, while our powers of x are descending. So now that we figured out that pattern, we can get this thing done, right? So we have x to the 0 power. This one should be a to the first power, x to the second power. This one should be a to the second power, x to the first power. And this one should be a to the third power and x to the 0 power, right? So that turns out being our constant term. And we're done. But does it follow the pattern? Looks like it. All right, so now we're going to predict, without performing division, whether or not the divisor will divide into the dividend without a remainder for the following problems. If so, we're going to find what the quotient is. We're going to check our answer. Okay, so let's do this. If you're going to guess at this, you might see that what you have in your numerator is difference of squares. Right? And we have seen already, right, that if we're going to look at difference of squares, right, for instance, let's look at this in parallel, x squared minus 4. This is factorable, right? We can write this as x plus 4, x plus 2, apologize, and x minus 2. So then it would make sense that I could write this as x minus a, x plus a, right? So if that's the case, then are we going to have a remainder? And the answer is no, because x plus a is a factor of x squared minus a squared. So when you divide that, you should actually get just x minus a, right? Okay. Well, it's less obvious for difference of cubes. Right, which is what we have here in B. We have difference of cubes here in B. Do we remember offhand what the formula for difference of cubes is? Maybe not. Maybe you've never seen it before. In which case, I would really like to actually not do what Eureka is telling me to do, and go ahead and divide this thing out and see what kind of result we get. What's going to happen? I'm going to go with reverse tabular method. So that means that I'm going to have 2 rows and 3 columns. There it is. And over here I'm going to have x cubed. I'm going to have the 0x squared and a 0x and a negative a cubed. And then over here we'll have our x and then our positive a. And let's go through this process. So this is going to be x squared, which means that this is going to be ax squared So this is going to be negative ax squared, which means this will be negative ax. So we'll have negative a squared x here when I multiply. What will I have to have here? Positive a squared x, so that I can get that 0, right? And then what did I multiply x by to get a squared x? Well, that's got to be a squared. And then a times a squared is positive a cubed. Okay, look, these guys don't match. And it turns out, and we'll learn about this later on, when we don't have matching numbers there, what that means is there is a remainder. And at this point, we don't need to worry about what the remainder is or anything like that. What we need to recognize is that if there is a remainder, then whatever we are dividing by is not a factor. And to put that into more easy to grasp language, right? 12 divided by 3 is 4, right? But 12 divided by 5, well, that doesn't come out to a whole number, right? There's a remainder. So if I was going to write this as, say, a mixed number, right? We're looking at 2 and 2/5, right? Our remainder is 2. So this was our remainder. Is 5 a factor of 12? Definitely not, right? And one way that we could show that is by saying, hey, there's a remainder. It doesn't go in there evenly. And that's the same thing that we're saying here with this x plus a. We're saying that x plus a doesn't divide x cubed minus a cubed evenly. And therefore, x plus a is not a factor of x cubed minus a cubed. Let's go ahead and look at this next one. And let's use our long division method. Okay, we're going to divide x squared plus a squared by x plus a, but of course, I need a placeholder in here. So that's 0x, and then we have a positive a squared is essentially our constant term. So this is going to be x squared. I'm going to multiply this back out. Right, we wind up with a positive number there. I'm going to switch the signs and then add. So I'm going to wind up with a negative ax here. Drop down my a squared. What do I need to multiply x by to get negative ax? Well, that's going to be negative a. When I multiply that thing back out, I wind up with a negative ax here. And I wind up with a negative a squared. When I change the signs and add, I get a 2a squared here. Remember, before we were getting 0. There's a remainder. What does it mean if there's a remainder? We just talked about it, right? That means that x plus a is not a factor. Of x squared plus a squared. And I don't know if you recall, but possibly you recall, there's definitely a rule, right? There's a formula that we can use to find difference of squares. But there's no sum of squares formula. And so that makes sense. All right, and then I'm just going to go ahead and let the cat out of the bag on D and tell you that x cubed plus a cubed, that's sum of cubes. Now, it's different than squares, right? There's no difference of squares. Oh, sorry, my bad. There is a difference of squares, but there is no sum of squares. However, cubes are different. There is a rule, or there's a property for describing both sum of cubes and difference of cubes. Turns out that the property for sum of cubes is going to look like this. So what does that mean? If I can express these the same, right? That means that x plus a is a factor of x cubed plus a cubed. And that's it. I mean, just because I can express this property, that means that it's true that I can divide those things. Okay, here we go. Let's find this quotient. Starting to get a little more different, right? A little more different. Pretty sure that's not good. Anyhow, what was the pattern that we came up with? Right? Remember at the very beginning we had come up with the pattern, yeah? So what is our quotient going to be? So when n equals 2, what will our quotient be? Just x. Plus 1. Okay. And then when it's 3, remember with x squared plus ax for 4, x cubed, and be thinking about the pattern as we go through this. Remember, this should be the a, right? So we have the first power here, so this one's got to be the second power. And then x is also going to be, what, to the second power. And then the a is going to be the first to the third power here, while x is to the first power. Lastly, a will be to the fourth power, while x is now to the 0 power. So x to the 0 power, you don't see it because that's 1. Alright, I'm sorry, I was jumping ahead. In my mind, I added an a there because I'm currently thinking ahead in the lesson. So there's no a. I was trying to generalize this when it's not 1. So we're not looking at a to some certain power, but 1 to some certain power, right? So this is x squared. So this is 1 to the 0 power times x squared plus 1 to the first power times x. There we go. And then we wind up with our constant term of 1. Alright, so we're going to start with x to the third. And then we'll wind up with an x squared plus x plus 1. I was jumping ahead, putting that a in there. So what I was showing you was x to the n minus a over divided by x minus a. And we're going to get there. Just jumped ahead in my mind for a moment there. What is the pattern? What's the pattern we're seeing there? All right, it looks like this first one is, what? It's x to the first power times, and we're going to put in the stuff that you don't see there, these coefficients, right? This is times 1 to the 0 power. And then we wind up with x to the 0 power times 1 to the first power. Then the next one in our pattern, we wind up with x squared times 1 to the 0 power plus x to the first power times 1 to the first power plus x to the 0 power times 1 to the second power. And it's kind of weird you don't see that happening because 1 doesn't show you those squares, right? 1 squared is 1. So you don't see the pattern coming out as you go, but it's there, and it's going to come out especially when we look at this next one. So let's write an expression that's equivalent to this for anyone. Well, it looks like we've kind of started the groundwork on this, right? So what's going on with n? All right, so let's look at this. Let's write this equivalent expression. We're going to use this pattern. All right, it looks like for the first one, right, we said n was 2. Yeah? So let's look at it. So when n is 2, we have this pattern going for n equals 2, right? So what's the power of 1? What's this x to the first power? What is that? Isn't that 1 is it's 2 minus 1, right? Okay, all right. So then can I say, I should be able to say, that this is x to the n minus 1, right? Okay. And then what's going on with our coefficient? Right? So what's going on with the 1? Well, what's going on with the 1 is the power is ascending. And we'll deal with that. We'll come up with a super general equation for this as we go on. But for right now, it doesn't matter if the power of 1 is ascending because it just gives us 1. And what we really want to start seeing is this pattern that's forming. Right? And we go all the way down to x to the first power plus 1, or let's call it x to the 0. All right, so we'll keep the subtracting powers until we get all the way to our x to the 0 power. And that's all for that. We're actually going to push this and extend it even further in lesson 7 so that we can come up with all kinds of cool things we learn about prime numbers. Well, that was a long bell, and ways to extend these even further as we go. So be ready on the calendar. I will put the assignment for next class. You guys have a great one. Thanks for watching.